Welcome to today's lesson. It's a continuation of previous lesson on radioactivity. We had discussed radioactivity in details, and we said it is the spontaneous degradation of unstable nuclides. And we had said nuclear radiation, when unstable nucleus decays, they emit particles and energy. There are three types of nuclear radiation. One is alpha particles, two beta particles, and gamma rays. In the previous lesson, we had discussed about alpha particles. Today, we'll be discussing about beta particles and gamma rays. In our previous lesson, we said an alpha particles resemble a helium particles. When it is lost, the mass number decreases by 4 and the atomic number decreases by 2. For beta particles, the beta particle resemble an electron with a mass number of 0 and an atomic number of -1, which resemble the symbols shown in the diagram. The beta particles has a negative charge. They are the smallest of the radiation particles, much faster and more penetrating than the alpha particles. Initially, we had said that they can be stopped by a sheet of aluminum foil or a piece of wood. When unstable nuclide disintegrate to lose an electron, the mass number remain the same, but the atomic number increases by 1. For example, when an iodine disintegrates to form the xenon by losing an electron, the mass number will be 131 minus 0, which gives us 131, while the atomic number will be 53 minus 54, which when unstable nuclide disintegrate by losing an electron, the mass number reduces by 0, while the atomic number increases by 1. For example, when the iodine disintegrates to form the xenon by losing an electron, the mass number will be 131 minus 0, which gives us 131, while the atomic number will be 53 minus 1, which gives us 53 plus 1 to gives us 54. The total mass and the charge of the nucleus and the electron emitted at the end are the same as the beginning, but the number of protons or the atomic mass will increase by 1. For gamma rays, they are in form of energy, and we say they are electromagnetic waves. They are usually emitted from a nucleus when an alpha decay or a beta decays occur. Gamma rays have no mass or charge and travel at the speed of light. They are deepest penetrating of radiation, but is not as damaging to living tissue as alpha and beta. They require dense or thick materials such as concrete blocks or lead to stop them. In summary, we've said that alpha particles have a greater charge and mass than beta particles, and therefore they are slow and they have high ionizing power. Alpha particles travel about 7 cm through air and are stopped by a paper or clothing. For beta particles, they have a charge, have 1 as a charge and no mass. They are more penetrating than alpha particles. Beta particles travel about 1 meter through air but are stopped by an aluminum foil. While for gamma rays, we've said they are magnetic wave or they resemble energy. They have no charge or mass and are the most penetrating because they move at a very high speed, same as the speed of light. They are blocked by very dense, thick materials such as lead or a few meters of concrete. For unstable nuclide to disintegrate to form a stable nuclide, we say this is termed as radioactive decay. In radioactive decay, there are particles that are emitted, and these particles, we'll discuss them, the alpha particles, the beta particles, and sometimes emission of energy, the gamma rays. When this happens, the mass of unstable nuclide disintegrate into a half, and this we term it as radioactive half-life. Radioactive half-life, we can define it as the amount of time it takes for half of the nuclei in a sample of an isotope to decay, or in another term, the time taken for unstable nuclide to decay by half its mass is what we are referring to as radioactive half-life. For example, if we consider an isotope of hydrogen, tritium, its half-life is 12.3 years. For it to decay to form a helium isotope, it will take 12.3 years for its mass to reduce by a half. For example, if I have this sample of isotope of hydrogen with 20 atoms, for its mass to decrease by half to form 10 atoms, it will take 12.3 years. This 12.3 years is what we are referring as half-life, the time taken for hydrogen to decrease its mass by a half. So we can say that each half-life will take 12.3 years. So if we have 20 atoms, it will decrease by half to 10, then from 10 to 5, and each decrease is what we are referring to as half-life. Let us look at an example of a radioactive half-life. If the half-life of 100 grams of a radioactive isotope is 8 years, how many grams will remain in 32 years? How many grams will remain in 32 years? First, we have to ask ourselves a question. How many half-lives are there in 32 years? If one half-life of this radioactive isotope is 8 years, for its mass to decrease by half, it takes 8 years. Now, how many half-lives are there in 32 years? It will be very simple. We take 32 years, we divide by 8 years to know how many half-lives are there. And here we'll get 4 half-lives. Therefore, the first half-life will be for the mass to decrease by half to 50 grams. That will be the first half-life. The second half-life will be from 50 to 25. Then the third half-life will be from 25 to 12.5, and the last one, or the last half-life, will be from 12.5 to 6.25 grams. So that will be the fourth half-life. So our answer will be 6.25 grams that will remain in 32 years. Since in 32 years we have 4 half-lives. We can still illustrate the information above in a graph. If in our vertical axis or the y-axis we have the mass or the percentage of our isotopes, then in the horizontal axis or the x-axis we have the number of half-lives. If initially we had 100 grams or 100% of our mass, then half of it, which is the first half-life, will be 50 grams. Then the next half of it, which is the second half-life, will be 25, and so on until the fourth half-life, where we'll have 6.25. So the above information, we can be able to represent it in a graphical as shown, since we've defined that a half-life is the number of time or the time taken for half the mass of unstable nuclide to decrease by a half. Radioactive decay or half-lives has been used in radioactive dating, using known half-lives to date certain rocks, fossils, and other materials. For example, the carbon dating has been used to determine the age of fossils and even some plants that died long times ago. Also, uranium dating is used to date some rocks that contain small amounts of uranium. Our next subtopic is nuclear reaction. This involves nuclear fission and nuclear fusion. Nuclear fission is the process of splitting a nucleus into several smaller nuclei. The process of splitting a nucleus into several smaller nuclei. Only large nuclei, such as uranium and plutonium, undergo fission. A neutron collides with a large nucleus and split into two. Some of the mass actually converts to a tremendous amount of energy. For example, if I take a metallic ball, bombard it with clay or a mass of stone, then the stone breaks into two equal parts with release of smaller particles and at the same time energy. We can term this as nuclear fission. For example, if I have uranium, bombard it with a neutron, a fast moving neutron, then our uranium, since it is unstable, it is disintegrate into two, forming krypton and barium and barium, and release of neutrons and energy. We term this as nuclear fission. Nuclear fission can undergo a chain of reaction. When a reaction fission takes place and other fast moving neutrons bombard other unstable nuclides that have resulted, then a chain of reaction can undergo or can take place. Critical mass, or the amount of material that is needed to sustain a chain reaction, must be there for a chain reaction to take place. Then it means that if we have unstable nuclide, this unstable nuclide can be bombarded into neutron, breaks into two, then these two, if they are still unstable and bombarded again with the neutron, they can split further and further. Then we say a chain reaction has taken place. Nuclear fission can be used to generate electricity. You've heard of countries that use nuclear energy. In this case, a nuclear fission is used, and elements such as uranium-235 is used in this case. As the nucleus split tremendously, we've said energy is released. This energy is used to produce steam that in turn turns turbines, which rotates an electric generator to produce electricity. We have advantages and disadvantages of using nuclear fission to generate electricity in some of the countries, or a source of electricity. The advantages is does not release pollutant like fossil fuel such as coal or petrol products. 2, provides about 1,000,000 times more energy compared to other fossil fuels. We also have the disadvantages or limitation of nuclear fission. 1, radioactive material could be released into environment in an accident. 2, disposal of waste material is expensive and difficult. 3, uranium is a non-renewable resource. Our second type of nuclear reaction is nuclear fusion with a U, nuclear fusion. When two nuclei of smaller mass are combined to form one large nuclei, we say it's nuclear fusion. When two nuclei of smaller mass are combined to form one large nuclei, we say, or we term this as nuclear fusion. It produces more energy than nuclear fission. The temperature must be extremely hot in terms of degrees Celsius. For nucleus to be moving so fast that they get close enough for fission to occur, then it means that these particles must be traveling at a very high speed for them to bombard together, fuse together, and as a result, they'll end up producing energy. Still, nuclear fusion can be used to generate electricity. When two small nuclei, such as hydrogen and helium, combine at a very high speed and at a very high temperature, they can be able to generate energy, release huge amount of energy that can in turn be used to produce steam, and the steam be used to turn turbines, and turbines can also be used to generate electricity. Nuclear fusion has its own advantages and disadvantages in production of electricity. Advantages is that it uses hydrogen as a fuel, which is very abundant on Earth. Number 2, the product is helium, a non-radioactive and non-polluting element. Number 3, most concentrated energy sources are known. But we also have the disadvantages, which 1, occurs only at high temperature of millions of degrees Celsius. 2. Uses more energy to produce the reaction than energy given off. 3. Containment of the reaction will be extremely difficult. In summary, we've said that nuclear fission is or happens when a fast moving neutron bombarded with unstable nuclides, and splitting the unstable nuclide into two stable nuclides together with neutrons and production of energy. While nuclear fusion happens when two nuclei bombard together and fuse, producing energy and other small and one large particle. Then we say this is nuclear fusion. To sum up the topic, let us discuss about uses of radioactivity. 1. It's used in treating cancers. And this happens when a radioactive element is used to kill cancer cells. Number 2, it's used in internal inspection. Sometimes a radioactive element is introduced into our body so that it can be able to do or expert can be able to carry out inspection inside our body without doing operation. Number 3, radioactive element is used in dating of artifacts. This is determining the age, for example, of fossils. Number 3, it's used in tracing, and in tracing, this is where it is used to determine or to inspect leakage pipes, for example, for fuels. We can be able to introduce a radioactive element into fuels or other pipes so that it can be able to detect where we have leakages. Another use, it is used in smoke detectors to prevent occurrence of fire. Another use of radioactive element is in sterilization. We've said, for example, the gamma rays can be used to sterilize surgical instruments that are being used in hospital. Another use is in food irradiation. This is where food are preserved by irradiating them with energy or radiation so that they can be able to be preserved, because this one kills germs and other microorganisms. Another use is thickness or monitoring thickness. For example, determining the thickness of iron sheet and papers. They can use radioactive elements. And the last use of radioactive element is in generation of energy for electricity purposes. Thank you.